Let's solve another problem 14-38 of our Fibler, and in this problem we have a square and it has a weight 60 kg. It is moving from A to B. We have provided with the curve and the height of this point A. So we have to find the speed when he reaches at point B, and also we have to find out the normal force exerted on him by the slope at this point. So uh, this is a uh, frictionless surface. That is why we will neglect the force of friction, and we have to find out the force and the velocity at point B. So in order to solve this problem, we will use the work energy equation and the related equation to calculate the unknown variable. So we have the work energy equation, which is TA to TB. So we can write it as TA plus sum of all the work done from A to B is equals to TB. So we have initial speed, so it means we have initial kinetic energy. So this is half mass of this square is 60 kg. We have the velocity, which is 5, plus work done by the forces uh, on the sky. So this is the simple. The sky is moving due to its weight. That is why weight is only the force which is acting on this sky. So that is why we can use the relation mgh, or the work done by the weight. So mass is the 69.8, and as it is moving downward, that is why it is positive, and we have to calculate the distance height. So over here, what is this value? So we can calculate it by simply putting the value of 0 in this equation. We will get the y. So when you will solve it, you will get 5. So the distance covered from this position to this position, that is why we will get at this position, this is 5 meters. That is why we can put over here 10 meters, right? And we have to calculate the velocity at point B. That is why it is half 60 VB square. So when you solve this equation, you will get VB is equals to 14.9 meter per second. So did you see that it is very convenient to use the work energy equation, so that we can calculate the initial final velocity easily. Now in order to calculate the forces, we have to use the Newton second law of motion, so that we can calculate the normal force exerted by this surface on this sky. So we will draw the free body diagram and will analyze the forces. Now at this point, when it reaches at point B, then we have a force which is a normal force, and we have a weight which is only applying in this direction. So we will as this is the as the body moving towards B, that is why this point, this is the uh, tangential direction, and this is the normal direction. That is why we can apply sum of all the forces in normal direction is equals to MAN. So in upward direction, we are taking forces in positive, as positive. That is why we can use the equation, and this is N minus W is equals to mass, which is 60. AN is V square by rho, right? So VB, which we have calculated in the previous slide, now we will calculate this rho because the equation of the curve is given, so you know the relation that how we can calculate this rho. And we have to calculate this normal force only. So weight is provided to us, or we can calculate it. So when you uh, uh, apply the equation and calculate the variable, then you will get n is equals to 1.2 kilonewton, right? So this is that is how we can solve this problem. Now let's try another problem, which is 14-21, and in which in this problem we can see that both bodies are interconnected with each other, and they are connected with each other by a rope or a cord. So we have provided with the weight of the block A, which is 60 pounds, and the block B having 40 pounds, and the coefficient of friction between these two blocks are between the block and the surface is zero point 0.1. So we have to include the friction in our analysis. So we have to find out the speed of the block A when body or the block B moves 2 feet in the upward direction. So uh, we can apply the work energy equation when for the system of particles, and in this problem you can see that we have our whole system in which we have to uh, separate bodies which are interconnected with each other. So the work energy equation can be applied for an individual particle, but also it can be applied for the system of particle. The minor difference is that we will include all the kinetic energy and all the work done by the forces on in the bodies which are included in our system. So let's solve this problem and see that how the work energy equation can be applied for the system of particles. So as this is the dependent motion analysis, or you can see here that these bodies, the motion of one body is depend on the motion of the other body. So we have learned this in the dependent motion analysis in chapter number 12. So in order to find the velocity or a kinematic parameter, we have to first define our datum, then we will calculate the total length of the rope, and then we differentiate with respect to time to get the velocity, and we again differentiate with respect to time to get the acceleration. So similarly, as we have to calculate the velocity of A, which is depend on the velocity of B, that is why we use the same relation which we used in the chapter number 12. So you can see over here that this is the uh, SA, and this is the position of the block B SV. So the total length of the rope will be 2SA plus SV. So you can see over here. So when you solve it, you will get the velocity of body B is minus 2 VA. Now the negative sign is representing that when body B moves upward direction, then body B moves in the downward direction. So velocity of body B is twice the velocity of the velocity of A. So let's move ahead and apply the find out the forces on our bodies. Now separately we have draw the free body diagram. So in this diagram you can see that this is the body A, this is the body B. Weight, tension, friction force, and the normal force is acting in our body A. Similarly, we have a tension, weight, friction force in this direction, and the normal force in direction is applied on our body B. So we can in order to calculate this mu or the friction force, or the normal force, we uh, uh, took the help from the Newton's second law of motion. So when we apply the equation in the y direction, then we will get for body A, this the normal force is WA times the cos 60, right? Similarly for body B, this normal force is this. Now let's apply the work energy principle. So this is our system which have the two particles, right? So we will uh, include the kinetic energy uh, of the A and B. Similarly, we will include the forces applied on body A and B, and finally the kinetic energy A and B. So here this is our equation. So in this equation, this is the component of the kinetic energy alone, right? So this is the half mva square, va1 square, which is the initial velocity of body A. Similarly, this is the initial kinetic energy of body B. Now the work done by all the forces on body A and body B. So this is the term which is used for it. So we have this uh, weight component of the force. Similarly, we have the work done by the tension, and we have the work done by the friction force. So these are the individual forces multiplied by the distance. So we take this distance common, and these are the forces. Similarly, we adopted the same procedure for this body B, and this is the final kinetic energy of body A and body B respectively. So we have used this relation, velocity is given to us, and when we put the values in this equation, which is equation, this is our equation 1. So this is the equation 2 in which we have put the value for the variables. So by further putting the value and solving the equation, we will get the final velocity of the block A, which is our required result. So that is how we have solved the problem related to the particles, uh, related to the system of particles by using the work energy equation. Now let's discuss power and efficiency. So you all know that power is the rate of doing work, and for suppose this is the work and this is the time. So you can put the value of the work, which is F dot dr, and when you divide by dt, you will get this dr by dt is the velocity. So we can write power as the dot product of the force and the velocity. So this is the scalar quantity, and we have to take the uh, component and the force, the component of the force and the velocity which are in the same direction. uh, and the unit of the power is watt, and which is equals to joules per second. Similarly, efficiency can be defined as the ratio between the power output to the power input, and if we can talk about in terms of energy, then this efficiency can be the energy output to the energy input. And also the efficiency of the machine is always less than 1. So this is the power and the efficiency. Now let's solve some problem related to the power and efficiency. Now let's solve a problem related to efficiency and power, and we are going to solve the problem F14-12, in which you have a block and the motor, and this motor is hoisting this block having the mass 50 kg with the velocity and acceleration of 6 meter per second, 12 meter per second, and 6 meter per second square respectively. We are also provided with the efficiency of the motor, which is 0.8. So we have to calculate the power supply to the motor at that instant. So we know that efficiency is equals to the power output to the power input. So in order to determine this supplied power, we have to first calculate the output power, right? So we know that the power is equals to F into V. So this is actually the velocity of that point which is acted upon the force F. So in this case, this force is the tension force which is created due to this weight of the block which is moving in the upward direction. So let's find out this force, and after that we will calculate the uh, input power which is required to supply to the motor. So in order to calculate this force, we will use the Newton's second law equation. So this says that F is equals to ma, right? And the force is in the upward direction. So at this point, we have two forces. This is the tension force, which we will uh, experience over here at this point, which is moving with the velocity 12 meter per second, right? So here we have a weight minus 2t. The weight, the mass is 50, and this is ay, right? So as we have to calculate the acceleration by which it is moving in the upward direction, so we can see over here that this is the dependent motion analysis. As the point B moves upward, it will move in the upward direction. That is why this is a problem of a dependent motion analysis which we learned in chapter number 12, and we have a procedure to find out the kinematic parameter in this case. So in order to calculate this acceleration, first we will define our datum. This is our datum. We will uh, define the position of a certain point. So this is SP, and this is the SA, right? So in order to calculate this acceleration, we know that we will find out the total length of the rope, which is 2SA plus SP is equals to total length, right? We differentiate it, and we again differentiate it. We will get 2A plus AP is equals to 0, right? So in this way we will get this A as minus 3 meter per second square, and minus sign indicates that it is moving in upward direction. So we are taking a direction in upward, positive upward direction. That is why we will put the value of AY as 3, and when you will solve it, you will get the tension force 320.3 newtons, right? So we will put this value in equation. So we have a force in form of tension, so this is 320.3, and it is moving with the velocity 12, right? When you solve it, you will get 3844 watt, right? Now we have to find out the power supply to the motor. That is why we will use this pi is 3844 divided by zero point 0.8, so we will get 4.8 kilowatt. So this is the power which will be supplied to this motor in order to hoist this block in upward direction. Let's solve another problem, which is 14-58, and in this problem you can see that we have a block which is attached by the spring, and we have a variable force which is F as a function of this displacement is given to us. The surface is not smooth, it has some friction, and coefficient of kinetic friction is given. So we have to determine the power developed by the force the instant the block has moved 1.5 feet. So the force is given to us, the distance is also provided, we have to calculate the power. So we know that in order to calculate the power, we have a formula that Fp is equals to F into V, right? So we have to this is the velocity of the particle on which is influenced by the force F. So uh, we have a force which is 40 plus s square, and s is given to us. So we can say that our F is 40 plus 1.5 square. So we will get F is equals to 42.2 pounds, right? Now we have to calculate the velocity. So in order to calculate this velocity, uh, we will use the work energy equation, because velocity is involved in this equation. So by using the work energy equation, we have T1 plus sum of all the work done from moving the particle from position 1 to 2 is equals to T2, right? So for calculating the work done by all the forces, we have to draw the free body diagram, and we have to see that what are the forces which are acting on our block. Then initial and final kinetic energy will be needed. So as the block is starting from the rest, that is why we have zero kinetic energy, and finally we have some kinetic energy uh, which is half mass is 50 divided by 32.2 into v square. So velocity will be needed, which is the velocity of this uh, velocity used in this equation, right? So now this is the term which we need to calculate. So let's move ahead and solve for this work done. So at this point, we have a weight, we have a force of spring which is applying in this direction, and we have a friction force, and we have a normal force, right? So these are the forces which are acting on our particle. So in order to calculate the work done, we will use the work energy principle, which is sum of all the forces from 1 to 2 is equals to T2. So we have covered this initial and final kinetic energy. We are working on the work done by the forces. So first of all, let's take this force which is F and we will take the only component which is in the direction of the displacement. That is why as the block is moving in the right hand side and the force is also acting in this direction, that is why work done by this force is positive. So this is from 0 to 1.2, and we have a force which is 40 plus s square cos 30 ds. Now we will use this spring force, and this is negative, so we will use this spring force, and it is half kx square. So k is 20, so displacement is 1.5. So this is the work done by the spring. Now we are left with this friction force. So we know that friction force is mu kn. So in order to calculate this n, we will use the equation that sum of all the forces in y direction is equals to 0. So we have the relation that n minus 40 plus s square sine 30, and the weight, which is minus 50 pounds, is equals to 0. So from this equation you can calculate the normal force. So we will get n is equals to now let's start the new topic, which is conservative force. And conservative force is a force if the work done is independent of the path followed by the force acting on a particle as it moves from A to B. So it's mean that the work done by the force in a closed path from A to B and then back to A is 0. So it's mean that if the work done from going from A to B and then again from B to A, if the total work done is 0, then the uh, work is said to be conserved, and our, in this case, our force is said to be a conservative force. So so the work done by the conservative force can be stored in the form of the potential energy, and it can be represented by the potential function V. So we have two kinds of potential energy. One is gravitational potential energy and the elastic potential energy. So the total potential energy of our body is the uh, sum of these two potential energies. So we know that the potential energy is due to the position of the body. So work done by the gravitational force is a conservative force, and the work done by the gravity will be stored in the form of the gravitational potential energy. Let's suppose we have a datum. So if our body is moving is above the datum, then it will have the positive potential energy, and if the body is below the datum, then it will have the negative potential energy. Spring force is also a conservative force, so the work done by the spring is stored in the form of elastic potential energy. So if we have the our spring at the unstretched position, and if we displaced our particle from the datum, then it will have the potential energy which is equals to the half k s square, where s is the deformed length of the spring. So as it has involved the square sign, that is why we never have the negative elastic potential energy. So I request you to kindly uh, read the related topic in your book and try to solve this quiz, and also this attention quiz. And if you have any problems, so you can discuss in the live session.